In this video, I'm going to talk about streaming speech-to-text services that are able to make captions pretty much instantaneously. And the model I'm going to show you is Kyutai, I think that's how you pronounce it, from the French AI company. They also have developed Moshi, and actually the techniques that they use for this text-to-speech model, or rather speech-to-text model, are based on the same kind of principles. Now, there are big advantages to this approach to using Whisper. If you want to do transcription, what you'll find is that the transcript is going to be a lot faster and you're going to have a lot less latency. Also, you'll be able to serve many more requests than is possible with Whisper, and I'll get into the technical reasons for why that is the case. Alors, je vais juste dire quelques trucs en français aussi, parce que c'est possible aussi que tout ce que je dis soit traduit. Bon, pas traduit ici, mais ce sera écrit sur l'écran, comme vous pouvez le voir. Et Moshi peut vous parler en anglais ou en français, ou bien un peu en allemand et aussi en espagnol, mais je ne vais pas essayer ça cette fois-ci. All right, so with that little demo, we're going to move on and talk through how this model works. We'll do some quick inference locally, just using my laptop because it's a really small model. Then we will look at how we can correct errors. So this is quite a unique feature that's possible only with Moshi. And probably I should turn off my transcription service here. But Moshi does allow you to correct in advance. If you have certain words that the model is not familiar with, it's going to be able to correct those by providing a little snippet of audio and also providing the text to go along with it. So if you say, I don't know what a word would be that would be unfamiliar with, maybe trellis, for example, it doesn't know that it's spelled with one L, but I could say in the word trellis, and then I could also give it the text, and it will actually transcribe that correctly. Now, the next one here is running a high-speed server. There's a very nice Rust implementation that Moshi have provided, or Qti have provided, so I'll go through that. Then there's the streaming and non-streaming text-to-speech service. Yeah, I want to talk about what the difference is. That's talking about Whisper versus Qti, why they're quite different architecturally, and why you can just get a lot faster if you do a streaming type model, a decoder model. And there are a few specific notes I'll talk about there on the theory side. A note about the delay. So Moshi has either a 0.5 second delay for transcription or 2 seconds, the smaller, the larger model. And then I'll talk about the semantic voice activation detection, which actually allows for extra speed up for reasons I'll get into. Now, I'm going to be going through the scripts in the advanced audio repo here. You can purchase lifetime access over on trellis.com/advanced-audio. There are a lot of scripts available for free in Moshi's repo here, Qti Labs Moshi. So I'll put a link to this in the description as well. So let's get started with the demo. I have cloned the repo. Let me reduce my screen size here and go back to the README right to the top here. You can probably just run this all on your laptop, even if you only have a CPU. I'm going to use Mac with MPS, but you can just use CPU. It's a quite small model and it should be able to do inference for you. So the very first thing I want to do is I'm going to run inference on my Mac. I'm going to use MLX. MLX is Mac specific, so this won't work with CPU, but I'll give you a PyTorch example in just a second that you could run if you don't have a Mac. And actually this requires 0 install because it uses UVX. It's like NPX. So we're going to use the run inference script, and we're going to use the 2.6b model. You could sub in the smaller model if you want. And we're going to transcribe this file here called LLM Lingo, which is an audio file that I've recorded. We can maybe just listen to, that there. It's a recording of me reading out some specific AI terminology from 1 year ago, actually. And it's got a lot of words that aren't familiar to the model. So you'll see that it doesn't transcribe some things correctly. That gives us an opportunity to fine tune, which I won't cover in detail today, but I probably will put out a fine tune video soon. So let's pass in this file here and run inference locally here on the Mac. And it looks like I'm in the wrong directory. I need to be in the speech to text Qti directory. But yeah, the reason I need to be in here is because that's the path I've given to my sound file. And you can see it's transcribing. It's streaming here, the transcription. A few things are correct, actually. Even Mixtral, it's getting. Now, granted, this model was probably tuned after Mixtral came out, so it's getting quite a few things. Fight 2 is actually Phi 2, and it's streaming at 20 tokens per second. Now, you can also run this in a notebook, and if you have just a CPU, you can run it in a notebook. You can set up a virtual environment like this here, just by running these commands. Install IPY kernel. And then if you open up the notebook, which is this inference notebook here, you can select the kernel like this. You can install Moshi. I think Moshi should already be installed. If you like, you can download this segment of audio from Kyutai, which talks about pancakes crêpe. And then we're going to import some of the loaders. The way I'm doing it here is not using transformers. It's using the raw Moshi implementation. So we're actually loading a text tokenizer and then the audio tokenizer, which is called Mimi. So we'll load that up. And then we're going to, using PyTorch code here, basically set up the padding, set up all of the tensors, and we're going to run the inference. And that should allow us to just print out the transcript here once it's complete. Now here you can see the device that we've chosen is MPS, but you could also just set this to CPU and this would work fine as well. So there shouldn't be any issue with that. It won't be quite as fast as the MLX implementation, and it won't be as fast as the Rust server that we'll see a bit later. But if you want to do a quick demo, this should work fine. And there we have it. So we have the transcript coming out here, and you can see this time trick C, it should be trick SY. So some little things that I'm going to show you how to fix in the next step, actually. So to do some more advanced inference, we're going to clone the repo from Kyutai, and we'll move into delayed streams modeling. You can just follow this by yourself, even if you don't have repo access. Set up a virtual environment once you are in the folder. I've already cloned, so I'm just going to move into that folder. And there are a few things that we can do here. One is we can just run on a Mac or a CPU. I can actually just run CPU here, and we can get a transcript. But this time we can get some word timestamps. So hopefully we'll see some word timestamps when I run this here now. Sometimes CPU can be faster than MPS, although the MLX implementation should be really optimized. So you can see we're transcribing here, but we're going to get some word stamps only after it's all done. And how does it get word stamps? Well, because it's transcribing token by token, and because there's a fixed delay of either half a second or 2 seconds between the audio and each token generated, you're able to just remove 2 seconds or half a second from the token generation time, and that allows you to timestamp it based off the audio. Like if you have the audio here, you know for a given piece of audio that there's a corresponding token that will be generated in half a second. And so you're able to map that back and get timestamps for every word. So there's kind of free timestamping if you're doing Moshi, which is not the case with Whisper, because Whisper will take a 30-second chunk and it will then transcribe. It has no idea of the exact timestamps within, apart from the fact that it does train it on segment timestamping, whereas you naturally get back the timestamps if you're just going to be doing a decoding type model like this. So you can see once it's completed, it's actually come up with all the timestamps here. Next up, I want to show you this feature, which you could call text-assisted transcription. It's really text and or voice-assisted transcription. The idea is that before it transcribes, you inject a word that is unfamiliar, either the text or you inject some audio that's unfamiliar. I have found that it really only works if you inject both. If you just put in a word it's unfamiliar with, it won't really transcribe it correctly. So let me give you an example, and it's based around that. I think it's based around Trellis. It's based around, let's see. Yeah, audio plus text prompting. Sorry. So this is text only prompting, but actually what I found is you really need to pass in a piece of audio and text. And what I'm trying to correct is this thing here, Trixie. So instead of being Trixie, it should be Trixie, Tricksy. So I'm passing in the correct text, and then I'm passing in a recording I've made. So I just recorded myself earlier saying this. Let me just increase the sound. Yeah, so that's the recording. If you do record and you need to convert it to a WAV file from, say, M4A, then you can just use this conversion script here. And then you'll pass in the prompt text and the prompt file. And you can pass in cut prompt transcript, which will clean up the fact that we're passing in these artifacts at the very start. But I kind of like seeing them, so let's just run here. And what we're hoping for is that it correctly transcribes the word Trixie instead of trick and then the letter C. Now this is not going to stream, it's just going to process everything. So it's going to take a few seconds, maybe about 11 seconds, and then we should see it come up. Okay, I was totally wrong on the 11 seconds. I don't know why I remembered that number, but it should come up momentarily. All right. So yeah, it actually has got it correct. And you can see there's this extra word Trixie appended at the start. That's the word that we injected. But the fact that we injected it with the audio is helping it to get this word correct. So this is really useful because the classic problem with Whisper is you get certain things that are transcribed with the wrong spelling. And yes, you can do find replace, but you don't know in advance exactly how the model is going to spell those incorrect words. So it's quite hard unless you pass the whole model, the whole transcript through some kind of LLM, and then you pass in some words that might need to be corrected, which also might be error prone. So this is a really nice feature that you're able to pass in little kind of tips here and then get it to fix it. For the next part of the video, I want to show you how to run a server. There's a fast Rust implementation that's been implemented by Kyutai. And what I've done is I've converted that into a one-click template, which you can get from RunPod. And it's actually what I showed right at the start of the video. If you just click that and then you pick a GPU, this is an affiliate link, by the way. So there is some small commission for Trellis if you use it. So you can put in here speech to text. Let's just put in speech to text Moshi and edit the template. What happens when you start this up is it'll start a PyTorch CUDA image, and it will then run an onStart command that will do a few things. So it will install Rust and Cargo. It's going to verify the installation, install the server, clone and update the repo, and then it's going to start up the model. So here it's going to start up the English-French model. So this is the smaller model that supports those two languages. And you could also start up the larger model if you want to change the commenting here. Then it will pass off to RunPod to the standard entry point. And note that you do need to expose TCP port 8080 because that is where the service is going to be running. So once you have it running, and I already have it running, what you're going to see is everything should start up here. And yeah, it's crashed because I just stopped it abruptly earlier, but it will start up. And then what you'll do is connect, and you'll be able to copy the TCP address here that maps to port 8080. So you'll copy this here along with the external port number, and then go back and scroll down to the client section. All of this here just describes how you could install by SSHing in and then running the installs manually. But you can skip right down to 7 here, copy this as I said, and then you can run any of these scripts here. So what you'll want to do is copy it into this here. And I think I might have one error here. This should be 8080. And if you like, you can check what device you have. So for example, on my computer, let me scroll up. I should have a number of microphones. Yeah, so I have, my iPhone. I've got a few other. The one I want though is this, well, potentially this microphone here, number 4. So I would just pick device number 4, and then I can run transcription. I can also run transcription and show the voice activation detection using -- show voice activation detection. And if you want to transcribe from an audio file, you can also process that. And you can process it in real time, so it will not wait for that extra half second or 2 seconds for the larger model. It will just immediately try to process as fast as the GPU allows, which is by increasing the real-time factor. This basically reduces the delay by this factor, I believe. So it will give you the transcript a little bit faster. than if it was waiting to receive every chunk in real time. Otherwise, it's only going to transcribe at the same speed as the recording is being played, plus that little delay. And yeah, that wraps up the server demo. It will take, by the way, it will take maybe about 3 or 4 minutes for the server to start up. So you will have to wait a little bit if you want to do that. But you should get very quick streaming performance like I showed right at the start of the video. Now, I want to make a few more theoretical comments here and talk about streaming versus non-streaming text-to-speech models. The summary is, if you want fast streaming, Kyutai speech-to-text is going to be a very good option. If you want really good quality, possibly Voxtral is currently the best model. It covers more languages than English and French, although it's a bit more European-focused, maybe Arabic as well. But the quality has now surpassed Mistral. Has surpassed Whisper. Voxtral has a 24B model, which is a lot bigger as well than the Whisper model, so that's why it has a very strong model. Voxtral also has a 3B model, which is a bit faster, but still very good compared to Whisper. And then the classic, of course, is using Whisper. So these would be my recommendations. In terms of streaming versus non-streaming, it's worth laying out the comparison between the options that are available here. So in terms of architecture, and this influences the decoding speed a lot, Whisper is encoder-decoder, Voxtral is decoder-only, and Kyutai STT is also decoder-only. This is a large reason why Whisper is quite slow. I'll talk about why it needs multiple passes to be able to do streaming, and it uses a lot of compute. Another key difference is the number of channels. So Whisper will take in some voice, it will output some text. Voxtral will do the same, and it will do that all in one channel. So you'll have voice, 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 text, 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 text. Whereas Kyutai actually splits these into 2 aligned channels. So you'll have the voice being generated here, and rather than have all voice and then all text, they're actually both aligned with a small delay. So it'll be voice and then text being created in parallel. In terms of throughput, Whisper is slow, not just because it's big. It's a bit bigger than Kyutai. I mean, it's bigger because there's about 1 billion parameters in the encoder and decoder, and the smaller Kyutai is about 1 billion. But it's really not just that it's bigger, it's that Whisper is not autoregressive. Whisper requires all of the input to generate an output. So the only way to make it autoregressive is to run the full history multiple times. So you would transcribe some audio, maybe the first 10 seconds, then you prepend that to the next 2 seconds, transcribe that again. So you need to recompute absolutely everything because it's not an autoregressive model. So you'll require a lot more compute just for doing a single sequence. It's like you were simultaneously doing 10s or 20 sequences if you're trying to use the Whisper model as an autoregressive one. So that's fundamentally why it's a lot slower. In principle, Voxtral is going to be faster because it's a decoder-only architecture. It just needs to generate one new token at a time as you're decoding autoregressively. But it's going to have some stability issues. Yeah, let me just explain that now. So if I have a piece of text, let's just say I'm talking and I'm saying the quick brown fox jumps. It's hard to know exactly what the next word is going to be without getting a preview of the next thing that I'm going to say. And it helps having this little buffer. Now, Voxtral does not have a buffer, so it will just take whatever audio I've said and it will literally transcribe every piece of audio in that, which means the very last thing that it's trying to transcribe is not necessarily going to be too accurate. Whereas with Kyutai, they've trained it so that there's a little delay, so it will never try and transcribe the last either half second or 2 seconds. And this tends to make it more stable in its outputs because if you only need to transcribe everything up until the last half second or the last 2 seconds, that means you're going to be pretty certain with the outputs. So the stability of the Kyutai model is quite good because it has this little delay and it doesn't try to transcribe the very last piece. Whereas with Voxtral, it's always trying to transcribe the last piece. So if you get a full transcription of audio to here, the very last piece might be quite inaccurate. Now, it'll be accurate if you're at the end of a sentence because it'll be used to the complete sentence. But when you're mid-sentence and the audio stops, it tends not to be quite as stable. There's one other point here to mention, which is timestamping. Whisper trains for segment-based timestamping. It actually does that by putting in, it's not exactly like this, but it puts in little tokens for the number of seconds or milliseconds. So it'll have the quick, and then it'll put in another timestamp here. So Whisper literally puts in timestamps for segments. By comparison, Qti does not do that because you already know the timestamping. You know that every word corresponds to the audio that's either half a second or 2 seconds before. So you automatically get timestamping for free in that case. With Voxtral, I believe it's also trained on segments, but there's going to be word timestamping coming. There is a way to get word timestamps for Whisper, and I'm not sure if this is how they will do it for Voxtral as well, but you can look at the attention maps for every single word. You can look at what previous tokens are being activated, and you can use that to try and estimate what the timestamps are for the words. So yeah, basically you can see when you have a sequence of audio, the audio here, if that activates certain attention, so it's basically referring to part of the text sequence, you can say, oh, if it's activating the text over here, probably that is the timestamp for the audio segment. So this is how you can retrospectively use attention, and this is how some Whisper libraries actually get word timestamps, even though natively Whisper does not output word timestamps, unless you trained it specifically to have a timestamp like this every word. One other thing, Qti has got voice activation detection built in. So when I stop like that, it might very quickly detect that that's probably the end of a phrase. And if it knows that's the end of a phrase, then it's still, remember, got that half second or 2 seconds that it hasn't transcribed. What it can do is it can just forward and transcribe that half second or 2 seconds that it didn't, because it knows it's the end of some kind of utterance. And if it's the end of some kind of utterance, it's not going to gain any more certainty by listening for a little bit more. So it can just plow through that extra half second or 2 seconds of transcription. So this actually makes it sound even faster, because normally with the small Qti model, it's going to sound like a half second delay, maybe plus some processing time. But when you get to the end of an utterance, it's not even half a second, because it's going to detect with a tiny detector that's kind of bolted on to the transformer. The tiny detector is going to say, okay, you've finished speaking. We're not even going to wait to transcribe the next half a second. We're just going to transcribe it right away, and we'll get back the final response. So the latency can appear even shorter when you get to the end of an utterance with Qti speech to text. Now, sorry, that was just a lot of talking. If you can see here, it's the Whisper paper from a few years back. This is how it's an encoder-decoder architecture. You take in 30 seconds of audio, you encode it, and then you feed it in cross attention with the embeddings of these start kind of tokens for the task transcription, the language, the start of the transcription. And these then are decoded. But yeah, the problem is, if you have a piece of audio that's only a partial piece, you need to feed it in, you need to get out the outputs, but then you need to take those outputs and you have to again recompute all of this here. You're not just able to append only the last piece back on. Well, you're not able to basically keep the full KV cache that you have within the transformers, because everything here is being recomputed. So yeah, this is the problem with doing streaming type approach in Whisper. If you've got the full audio, it's fine. You just do one pass through. But if you need to keep on repeating that operation, you're forced to go through it many times, which is equivalent to having multiple sequences. I just want to show you here the side-by-side streaming. So with Qti, you've got an audio stream. You've got a delay of 2 seconds for the larger model. This is the larger model, by the way. And the smaller model is about 1 billion parameters. With the larger model, there's a 2 second delay. So you'll have audio, and then the model is trained to output with a delay of 2 seconds relative to the audio, the text tokens here. The last thing I want to show is just a little bit about the training. So it's worth checking here. It's interesting that this speech to text model by Qti, it's actually trained, well, it's pre-trained on a lot of data, 2.5 million hours, and they're both trained on the small and the big model. And it's Whisper time stamped. So Whisper Timestamped is a version of Whisper that allows for more accurate timestamping by using a dedicated timestamping model. So basically QTI, the accuracy could not really be better than Whisper because it's coming from data that itself is generated by Whisper. So QTI's value here on the speech to text is really around the streaming. That's the value. It's not necessarily improving on the quality of what was already there with Whisper, because a lot of the data was essentially timestamped with the Whisper model. And then you can see here that the fine-tuning stages differ a little between the big and the small model. The smaller model, you've got 2,000 hours. The larger model, there's about 24,000 and then some more here. Another, it seems, 23,000 or so worth of hours. So more fine-tuning for the larger model, which provides better quality, but it's going to be slower. And that is it on this tutorial on speech to text. It's all about speed. I think QTI have done a very nice job providing something that offers differentiation to the Whisper model and even to the Voxtral model, just because it's got this delay built in. So if you want something fast for real-time transcription, I think it's a very good option. I will consider doing a fine-tuning video, so let me know in the comments if that's of interest. And in the meantime, also let me know if you have any questions right below. Cheers, folks.